I am happy to introduce Mr. Suresh Kirtipati, and he was my junior at IIT Kharagpur, and he did, of course, post-graduation in transport engineering from IIT Kharagpur. He has around 19 years of total experience. In that, 17 years of rich and relevant experience in the fields of highway engineering, planning and design, pavement engineering, and project management, including preparation of detailed engineering designs, drawings. He has extensively worked in the areas of highway design, pavement evaluation, pavement design, and construction of various projects funded by NHAI and international funding agencies like Asian Development Bank, etc. He has been extensively involved in technical feasibility, preparation of detailed engineering design for major highway and expressways. He is convergent with the current highway design practices like the high practices IRC, UK DMRB, NRA DMRB, and ASTO, and pavement design philosophies and maintenance practices. The maintenance practices. He has thorough knowledge and usage of latest highway design software like MX Roads, VAI, and Softex. He was involved in several pavement evaluation studies and was responsible for design of rehabilitation strategies for in-service pavement. He has excellent experience in all kinds of engineering data collection pertaining to highways using sophisticated equipment like total station and GPS. He was involved in several projects consisting of preparation of detailed engineering designs and drawings including horizontal alignment, vertical profile, super elevation design, pavement design, quantities and costing, route selection and alignment options, formulation of improvements options, prioritization, economic evaluation, sensitivity analysis. Acted as a team leader and overall coordinator in all activities of our highway engineering projects and involved in conducting site surveys to steering committee meetings and inception report to detailed project report preparation. He has conducted almost all types of highway and pavement surveys, including topographical surveys, road network inventory, pavement condition, deflection measurements, DCP tests, roughness survey using sophisticated equipment like rounders, test pit evaluation, and topograph surveys, and all kinds of traffic survey analysis. He published 4 technical papers. I can say it's a very good technical papers. So based on his work only, like we have right now the IRC 58 okay, 4 technical papers in Indian road concrete journals and various international conferences, and one of the contributors for revision of IRC 58 2011 code book, and of course the latest code book also IRC 58 2015. So I welcome Suresh for delivering his presentation. Suresh, please go ahead.
Thank you, Dr. Amar. Thank you, the co-organizers, for giving me this opportunity to present the stresses in concrete pavements. Are you seeing my presentation?
Yes, Suresh, but you just yeah, slide slow. You put it in slide slow mode. Yes, yeah, now okay, fine, good. Go ahead.
Yeah. I'm going to present only on the stresses in the concrete pavements due to various load conditions like self-weight of the slab and the temperature variation, nothing but a temperature gradients from the top of the slab to bottom of the slab, and third one was wheel loads. So if you see the presentation, the introduction and the structural behavior of concrete pavements under various load conditions, then the methods how to computate, how to find out the stresses in the concrete pavements, and then the latest developments of computer program KGP slab 2 with the finite element modeling with 8 noded and 20 noded elements, how that performing with 8 noded and 20 noded, and the modeling of temperature gradients. And finally, after the computer program is completed, generally, software also, when they do the computer programming, they will do the testing. On the same way, here we need to do the test or validate the computer program which we've written. And then finally needs to analyze the stresses which actually correlate to the field conditions. So these are the topics mainly I'm covering in this presentation. So coming to the introduction, nowadays concrete payments are using in both low volume roads and the high volume roads to provide maintenance free payments over a long period of the time. Maintenance free means maybe a period of 5 years or 7 years or 10 years. Compared to flexible payments, these are maintenance will be very less in the rigid payments, and no maintenance for the long periods. So people are preferring to go with the concrete payments nowadays widely in the country. In the various state governments or central government or private agencies also doing. So if you see here, I'm presenting a typical crust which normally used in the high volume roads. There will be a subgrade of 500 mm to the compacted to the compaction levels which are specified in the guidelines, and over that a drainage layer is the most important layer, is called as GSB, granular subbase, and over the top it is a DLC layer because we require a strong foundation beneath the PQC to stand alone without any deflections or deformations. And over the top, we are providing a separate membrane like a 125 microns. You call it as a plastic sheet, generally they call it as. And over the top, we are laying the PQC, rigid pavement of 250 mm to 300 and 320 mm. Because of this separation membrane, frictional stresses will reduce. Because of that one, a separation membrane is introduced between the concrete pavement and the DLC. Coming to the structural behavior of concrete pavements with the various load combinations, firstly we need to take care of the self-weight of the slab, how it affects the concrete structural behavior. And the second one was wheel loads. Under the wheel loads, how the CC pavements will behave. And third one is temperature variation through the depth of the slab is nothing but a temperature gradient, not the temperature differentials. A temperature. This is the temperature gradient along the depth of the slab. The top, what is the temperature, and the bottom of the slab, what is the temperature. The difference is this called as a temperature gradient. And then the fourth one was shrinkage of concrete at early age of construction. And fifth one was volume changes in foundation. These last two will have a less influence on the stresses in the concrete pavement. So these two, in this discussion, we are neglecting and we are focusing only on the top three. See, these are diagrams. If you see, there is a temperature gradient always in the slab. During daytime, nighttime, at any point of the time, slab will curl upward or downward, or sometimes it will remain same. Full contact with the whatever the foundation you call or with subgrade. If you see the daytime curling, it will be convex upward due to the self-weight. If you see the arrows, self-weight will always be pulling the slab to down. Because of this, there is a compression on the top and tension on the bottom. This is the temperature gradient. Because of this will occur. The slab will warp like this during the daytime, and coming to the nighttime curling, because of temperature drops, then the top of the slab will have the less temperature compared to the bottom of the slab. Then the slab will warp like concave upward. Just reverse to this temperature. This is the nighttime curling. So temperature will be there always. Because of the self-weight of the slab, the stresses are generating at the top of the slab and the bottom of the slab. I'll go into the second case. Here also temperature gradients are there always on the concrete slab. I'm looking only at the critical wheel load location I'm showing here. I'm not showing the other wheel locations, means wheels are placed exactly at the center of the slab. Then only this is the critical one for the bottom of cracking during the daytime. Tension will be at the bottom compression will be on the top. And during the night time, if you see, the slab will curve upward, and this is the critical locations, two locations of the load. If you place it here, then the cracks will occur here. So tension will be on the top and compression will be on the bottom. So how to find out the stresses in the concrete pavement? There are several methods in the industry to find out the stresses. Now here I am elaborating and taking only the theoretical analysis done by the Westergaard and the Bradbury, because these two equations or methods are broadly several, several years from early 90s to I think recent 10, 20 years back also these methods are used. So I am focusing only on these two approaches, how they did the analysis, what are the assumptions in the analysis, and its limitations and the shortcomings. So first I will go with the Westergaard analysis for load stresses. What are the limitations and assumptions he did in the analysis? First, he taken the thickness of the slab is constant, and second is each panel of the pavement is assumed to be fairly large and as yet uncracked. He taken a long and broad slabs and it is uncracked. And the load is, it means that the load is assumed in no case to be close to more than one edge or joint, only in one edge of the joint. Other edges or joints are assumed to be far enough away to have only a negligible influence on the stresses directly under the load. This is one of the important assumptions he taken. And the third one is the subgrade is always in full contact with slab. This assumption also plays a major role in the assumptions in the Westergaard equations. But in practical, the slab, when the warp up, warp down, some portion of the slab will lose the contact with the subgrade, or you can find our foundation, you can call it as, it loses the contact with the foundation. So this assumption implies that the reactive pressure between the slab and the subgrade always exists, no matter how the slab deflects. If the slab deflects upward at certain point, the reactive pressure at that point will pull downward. The subgrade will pull the slab down, means. So these are the limitations and the assumptions. With these assumptions, he given the solutions at three cases in 1926 in edge and the interior and the corner. Later on, the Westergaard himself is revised his equations and he modified the things in 1943 and 48 to correlate with the realistic pavement designs. Therefore, this approach is acceptable as a fundamental one for the design of concrete pavements. Most of the countries is used the Westergaard equations at the initial stages to find out the wheel load stresses and the temperature stresses. And in 1948, he himself modified the edge loading. Earlier, he taken half of the thing. Now he taken the full wheel load at the edge and the interior. These are the equations given by the Westergaard, and the latest stages is modified by the Teller and the Sutherland in 1970s, I think. And they given the equation for the edge loading stresses, how to find out with this equation. And the same equation is recommended in IRC 58 2002 for calculation of edge load stresses. For corner loading, again the Westergaard equations has been modified by the Kelly, and he given the equation in this form to find out the corner wheel load stresses. And the same equation has been recommended by IRC 58 2002 for the corner loading stresses. Coming to the Westergaard analysis for temperature stresses, and he taken some of the assumptions on this temperature stresses also to find out. See, these are the assumptions done by the Westergaard in 1926. Temperature varies linearly through the thickness of the slab, but if you see the practically, temperature varies non-linear. So he take an assumption that the temperature is varies through the thickness in linearly. Then the subgrade acts as a Winkler foundation consisting of series of springs. He taken a Winkler foundation model for the subgrade, means the a foundation. Slab and the subgrade are always in full contact. There is no gap when curls up or curls down. Always it is contact with the foundation fully. So with these assumptions, he given the solutions for three cases. Again, see, slab is infinite in both and x and y directions. It means the long and broad slabs. He analyzed it first with the long and broad slabs, but practically only the finite slabs we are doing in the field. But initially he taken long and broad slabs, and he given the moments and the stresses, tensile stresses for the slabs in x and y direction. And case 2 is slab is infinite in plus y and plus or minus x directions. So he defined means infinite in plus y means minus y he put is a finite one. Then he given the solutions for the tensile stresses in x direction and y direction. And case 3, he taken slab having finite width. He two directions he fixed, it is a finite width and infinite length. He given two directions infinite. So accordingly he given the equations for the tensile stresses for the temperature in x direction and y direction. And with this, there are some shortcomings of the to follow the Westergaard equations. These are the shortcomings. It cannot account for the nonlinear material behavior of rigid pavement systems. It overestimates the stiffness of concrete slab by assuming an infinite or semi-infinite plate. So these are the shortcomings. And later date, Bradbury came in picture, and he given the equations for the Westergaard formula only with simplicity. He modified the things and he introduced the Bradbury coefficient so that the Westergaard equations has been modified. Slab, he considered Bradbury slabs are finite, and he introduced the coefficients for the simplicity, because in the practical also slabs are finite only. You see 3.5 by 4.5 or 4 by 4.5 or 4.5 by 4.5. There are finite slabs only. For that purpose, he introduced one coefficient for the simplicity to calculate the temperature stresses. In both Westergaard and Bradbury, temperature gradient is considered as linear. There is no non-linear analysis here. They did both of them is a linear temperature gradient along the depth of the slab. If you see this this slide, limitations of Bradbury, here also he assumed the springs always contact with the slab when the curl upward or curl downwards. See the springs here. So always contact with the foundation. Slab is always contact with the foundation. This is the main assumption, and subsequently we will see how this will change practically. So he given the equations at the edge and the interior cases. These are the popular equations. Recent times also we are using this, and with the introduction of Bradbury coefficient to the temperature stresses. And if you see the shortfalls, means IRC 58-2002, it also recommends the Bradbury equations. What are the limitations of the IRC 58-2002? Wheel load stresses and temperature stresses are linearly additive. It means that you calculate the wheel load stresses separately with the Westergaard or some other charts are available, or on temperature stresses with differently with the Bradbury equations, and you club up both and then find out the maximum stress. This is the limitation of the IRS 58 2002. This condition is valid when there is a full contact between the pavement and the subgrade. Subgrade means always it is a foundation. Uh, Here it is on the top of the realcy. But generally this condition occurs only if there is no temperature variation through the depth of the slab. There is a constant temperature variation, then this is fine. If there is a temperature variation is linear, the contact will not be there with the foundation. There is a gaps will occur between the slab and the foundation in the real field conditions. So with these limitations, how to overcome? This is the only solution is available is to go with the computer programming with three-dimensional finite element modeling. There are many three-dimensional finite element modelings are available in the industry to correlate with the actual field conditions of the behavior of the concrete pavements. So here in this, I am going to cover the computer program which was developed in the IIT Kharagpur, named as KGP Slab 2, and it was written in the Fortran, and the program is models a finite slab, whatever size you want to put, you can make it 3.5 by 4.5, 4.5 by 4.5, whatever, and it is rested on the Winkler foundation, and it allows wheel loads as well as thermal loading. Wheel loads and thermal loading simultaneously at the same time it allows. And it takes care of full subgrade support as well as loss of subgrade support, means the foundation, full foundation support, or if it loses some foundation support also due to the thermal loading, it takes care of this program. And now I am going to how the program has been developed and how it is validated, and then stresses find out from the computer program. See, coming to computer program development. The computer program has been developed with two elements. One is with 8-noded element and another with 20-noded element. You see here, 8-noded isoparameter brick element. We have 8 elements, nodes here. 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 nodes available. This is the local coordinate system, and this is the Cartesian coordinate system. If we go to the 20-noded isoparametric brick elements, there are 8 corners or 8 nodes, and then every midpoint has another node introduced. So 9, 10, 11, 12, it comes to 20 total nodes here. So this is the Cartesian coordinate system. With these two, actually, we verified the computer program with 8-noded and 20-noded brick element with available solution, theoretically available solutions, so that our computer program is giving good results or not, or correct or not. We will validate the computer program. In this process, we taken a straight cantilever beam loaded with a point load of 10 kilonewtons at the free end in the vertical direction, and taken E equivalent to 2 into 10 to the power of 3 kilonewtons per centimeter squared, and mu equivalent to 0. And this cantilever beam is divided into 3 elements. In each case, means the 8-noded case also 3 elements, 20-noded case also 3 elements, and 5 elements in the 8-noded also, and in the 20-noded also. You can see it here. This is the 3 elements, this is the 5 elements. These are the 3 elements for the 20-noded, and this is the 5 elements for the 20-noded. And find it out the deflections and the moments what it is giving. If you see this slide, the comparison of vertical deflections from the far end means at the free end, deflection will be more in the cantilever. It's critical if you calculate, it comes to 0.2963. If you see here the results of three elements, 5 elements of 8 noded, or with 20 noded, 3 elements or 5 elements. It's coming the same, more or less. There may be a difference of 3 to 4%, not more than that. Sometimes it is giving 100% absolutely same as the theoretical and with the computer program. But if you see the comparison of bending stress will be more on the fixed end, the cantilever beam. At the free end is 0. So at the same way, we got the results also with the computer program has been compared with the theoretical values. Absolutely, it is matching with the theoretical values of the computer program. So going to another validation, we did the validation of the program in the plates with the different edge conditions. If you see here, there are 4 cases. Case 1 is simply supported. Case 2 is fixed at the one edge and 3 edges are free. Case 3 is fixed 2 edges and the other 2 edges are free. Case 4 is completely fixed. All 4 edges has been fixed and calculated the deflections on this, and these are all tabulated. This is the example which we taken. There are so many validations has been done. I am showing you only 1 or 2 only to know how the program to be validated. So we taken a 2 meter by 2 meter slab rested on a rigid foundation and having the modulus of elasticity 3 to 10 to the power of 5 kg per centimeter square. Pavements ratio 0.3. The entire slab was loaded with uniform pressure 0.1 kg per centimeter square, and the thickness of slab has been taken 15 centimeters. For thin slabs we taken. So these deflections came from the computer program KGP slab 2. If you can see here, case 1, 2, 3, 4 is the simply supported slab. See, there is only a change of 3 to plus or minus 3 to 4% plus or minus the vertical deflections came. Then we thought the program is running correctly, so we can go with the other analysis part. So during the analysis, this is the one of the findings why we went for the 8-noded and the 20-noded programming, because if you go with the more nodes, maybe it gives the accurate values. That is the thought. We thought that we will go with first 8-noded and 20-noded, then compare the both models, which is giving the best results. So we will do the analysis with that one. So during the analysis, it is found that the 20-noded program is taking greater time compared to 8-noded program, maybe 3 to 4 times more than the 8-noded programming. But this may be because of 20-noded element program has large amount of data in the form of nodal data and nodal connectivity as compared to 8-noded element program. Then we came to conclusion that which element we need to take, 8-noded or 20-noded. Then we did the comparison of 8-noded element and 20-noded element subsequently. See, we taken a slab which is resting on the Winkler foundation with the finite slab in the width and length also 3.55 meters. Is a square slab we taken, and we taken the single wheel loads varying from 8 to 16 tons, means 8, 10 or 8, 9, 10, whatever you want to take. 8 to 16 we varied with 2 additions of 8, 10, 12, 14 and 16 tons. And the subgrade modulus of reaction we taken 8 to 15. And for the various thicknesses, 200 mm, 250 mm, 260 mm, 280, 290, 300, we did the various analysis with the 8-noded element and with the 20-noded element with find the stresses and the wheel loads. And this is the beautiful results it came in both the cases. 8-noded, 20-noded, the results more or less same. There is no much variation on this one. If you take slab thickness of 20 or 30 or 25 and with different edge means subgrade reactions, K values, if you vary, and with the different single axial loads, if you see single axial loads 8, 10, 12, 14, 16. This is the 8-noded brick element, and this is the 20-noded brick element. There is no much difference on the stresses, edge load stresses, more or less same. And here also with the higher modulus of subgrade reaction also, there is not much changes for the 8-noded and the 20-noded programming. This, if you see the 30 centimeters thick slab, also if you compare with the 8-noded and 20-noded computer program results, more or less it's matching. So we concluded that 8-noded element is the which we need to take because of the faster results. There is no much change on the stresses in the 20-noded compared to 8-noded. So we taken the 8-noded element for the final modeling of stresses. Again, we verified the 8-noded program with the available solutions in our case in the cement concrete payments, Westergaard and Bradbury solutions we have available. So we compared with the Westergaard equation how it comes the stresses with the compared with the computer program. So Westergaard load stresses, what are the assumptions he taken by the Westergaard? Same assumptions had been loaded in the programming and taken the deflections and the bending stresses with the different runs with L by L ratios. If you see here, it is changing, and the B by L ratios are changing with the different combinations. We find out the stress is same. See, for any change in L by L or B by L, there is no change in the Bradbury, in the Westergaard equation, edge load stresses, bending stresses is the constant 41.81, 41.81. If you see the computer program is given different values, but it is matching almost all. If you see with the finite slabs, it is coming 41.81, it is 40, more or less same. So deflections, this is the interesting findouts. You can see here the deflections. Stresses are coming more or less same, but the deflections, if you see the deflections, 0.7 constant in the Westergaard, but in the KGP slab, if your L by L ratios are less, means the finite slabs deflections are more. If you go L by L ratios are higher, if you see the serial number 20 run number, then you see the deflections. This is the ratio of KGP slab and this. So this is a 14% higher results it came. Here, if you see, it's a 30% higher deflections came. And the same thing has been compared with the Bradbury also. And this temperature has been modeled in the FEM, finite element method. And the same assumptions we have been taken for the Bradbury, what he taken. The weightless slab is bonded to spring foundation to simulate the assumptions of Bradbury. And if you see this closely, these diagrams, this is the concrete slab, is the depth of the slab, is the uniform temperature change. Say, example, at the morning time, if you see the concrete having the uniform temperature all along the depth of the slab, say 25 degrees, and then if going on to the midday, it comes to say 45 degrees on the top, on the bottom maybe it comes to 25, say 5 degrees change here the change is 25 degrees. See, this is the uniform temperature is 5 degrees and the linear variation temperature is 25 degrees Celsius. So due to this linear temperature variation, we quantified the forces and applied on the nodes on this, converting the stresses acting over the faces into equivalent nodal forces and applied on the model and taken the stresses. This is the one example I am showing here. We've done a lot of combinations with the different sizes of slab and different thicknesses with different temperature variations. With this one of them I'm showing here. The rectangular slab having 3.5 by 4.5 size. Modulus of elasticity 29,430 MPa. Poisson's ratio 0.15. Coefficient of thermal expansion 1 into 10 to the power of minus 5 for degrees Celsius. And with the linear temperature differences of 13 degrees plus or minus daytime and nighttime at the same 17 degrees plus or minus, then 21 degrees plus or minus. Thickness of the slab 200, 250, 300, and the density of the concrete taken 2400 kg per meter cube. And with this, if you see the figures over here, the edge slab stresses received for thickness of 200 mm and modulus of separate reaction is 78 meganewtons per meter cube. This is the Bradbury, this is a straight line, the Bradbury stresses, temperature stresses, and these round ones was KGB slab to programmed, came the results from the program. And if you see the interior slab also with this particular slab thickness and with this particular subgrade reaction, it also both are matching. I can show you in the tabular form for the better understanding a comparison of stresses, edge warping stresses and also interior warping stresses with the different temperatures of 8, 13, 17 and 21, and in daytime, nighttime, plus or minus, more or less. Only here, if you see only 2% change, it means difference is there with the Bradbury and the KGP slab, two edge warping stresses. And the interior warping stresses, daytime, nighttime, there is only a 1% difference between the theoretical value and the programming values. So with this, we validated the program. You see the 300 mm thick slabs also is the only 1% change, means the difference is there. Here only 2%. So there is absolutely the computer program we can use for the different conditions which relating to the field. So with this validation, we went forward and did the modeling of the computer program with the realistic conditions by taking the self weight of the slab, loading the wheel loads, thermal loading, all together combinedly. There is no separate analysis for self weight, separate analysis for wheel load, separate analysis for thermal loading. No, all combinedly, three will act at a time. A more realistic model than the Westergaard and the Bradbury. So the computer program has been modeled for the finite slab on Winkler foundation. It allows wheel loads as well as thermal loading, and it takes care of loss of support also because of the thermal loading in the daytime and nighttime because of the curve warping up or warping down. Some portion of the slab will be loss of support with the foundation. This has been taken care in the modeling to measuring the deflections. If any deflection is coming in the slab plus or minus, we remove the separate reaction on that nodes. And again, the program has been done. The program has been modeled like that. It will iterate and come to the stage that there is no further iteration is required. So first time, if one node is loss of separate support, and then next time it comes 2 or 3, like that it will come to the standstill. And at that time, some of the nodes are not contact with the foundation, and others are contact with the foundation. It is the more realistic model has been developed, and extensive research has been done by the IIT Kharagpur. This is based on my thesis only, MTech thesis. In 2004, I completed. Later on, there are subsequent research has been done with the different conditions. I'm not talking on that one here. Only the basics, how the program has been developed for the self weight of the slab, taking the care of the curling, the daytime, nighttime. And these are the temperature gradients. This is the important one here introduced in this model, non-linear variation. If you see here, this is the non-linear variation. If you see practically also, if you measure the temperatures at different depths, from the top to bottom or bottom to top, temperature will vary non-linearly. This is the non-linear, and this is the constant temperature gradient. The term we divided into two parts. One is the constant varying of temperature gradient and the non-linear portion. And again, this non-linear portion has divided into three deltas, two deltas with full depth, linear variation, and one delta with the half, only top half portion we divided into this. With this, the model has been modified to take care of the nonlinear variations. And this is a critical wheel load, which I shown in the initial stage. During the daytime, curls downward, and the wheel load placed here. This is the critical one. This has been analyzed. Tension will develop on the bottom, compression on the top. This is called as during the daytime bottom up cracking. And this is the top down cracking during the night time. This is the critical wheel load locations. And with the different combinations of wheel loads and with the different combinations of the slab widths 3.5, 4.5, 3.8, 3.9, 4, 4.5, or you can take it as 3, 3.5, whatever you want. You need to make in the program itself, initially itself, you need to set the dimensions. Accordingly, you need to make the elements in the programming. Then it will take care of the length and the width of the slab. And these are the axial loads. And these are the different combinations: single axial, tandem axial, this is the tridem axial. These are the maximum stresses locations where you will get due to the wheel loads. So with this above FEM analysis, IIT Kharagpur did extensive research, and it was revised the code book in 2011 and 2015. As 58 has been revised. Some of the limitations of the approach and need future work. Why I am presenting this is there is a lot of research is required, even though most of the things are covered. Mostly, say I can say 80 to 85% is the accurate we achieve. There is a lot of research is required. The other 10 to 15% are the more accurate results. See here, the plenty of research is needed to determine the modulus of subgrade reaction K for different types of subbases for the pavement. There are different types of subbases. They have the subgrade reactions are different for the different subbases that we need to be validated. The assumption of that DNC subbase with plastic sheet on Winkler foundation may not be a correct one because DNC have higher shear strength. So Winkler foundation is not the correct, exactly fits is the practical one. Then we need to model that one foundation as a solid elastic mass. This is a more realistic one. We need to think about, need more research on this one. And need a field test also, FWD, to necessary to get the better parameters, the pavement design. And the temperature, this is one of the most important thing in the stresses, find it out. Temperature and moisture distribution in the concrete slab must be studied all over India for correct evaluation of stresses. Only we have the charts in the IRC in the state-wise or region-wise, but it may not be reflect the actual field temperature gradients. This required a lot of research on the temperature gradients. Then the reliability concept, this needs to be inbuilt in the design. So these are to be overcome, then our models will be more stronger to correlate the field conditions. With this, I'll take your leave. Thank you.
Yeah. Thank you, Suresh. Thank you for once again for accepting your invitation and your presentation. And I request participants, if you have any doubts, I request you just put it in chat box so that we'll take up. Yeah, Suresh, before that I have a doubt. In case of, if you can see, even IRC 58 2011 guidance as well as the recent guidance also, if you increase the modulus of subgrade reaction, right?
Yeah.
If the modulus of subgrade reaction is increasing, the up to after a certain limit, the stresses are decreasing. Why is that good?
See,
Stresses are increasing. Stresses are increasing, not decreasing. Yeah, subgrade.
increases, stresses will increase. Yeah.
Yes, yes.
So why it is because when the subgrade means the foundation is somewhat flexible, say when the slab walks upward or downward, if the foundation is flexible, then the slab will go into the foundation. So the contact area will be more. Because of that one, stresses will be less. If the subgrade reaction is less, it means it has the flexibility to allow the concrete slab go into the foundation and have the more contact area in case of low, subgrade modulus of reaction. If you go with the high modulus of subgrade reaction, means the foundation is very rigid. It is not allowing the slab to go down to the foundation to touch it. So when it warps up or warps down, more curl will be there, means more loss of contact with the foundation. So the stresses will be more. That is the reason it is giving more stresses if you go with the more subgrade reaction.
Yeah, yeah. Up to 300 mm, 300 MPa per meter, the stresses are decreasing. Then afterwards, it's increasing. That's what we have noticed with respect to the charts that are provided. Hello, hello, Suresh.
Yeah.
Yeah, that's it. So, any other questions, participants? Yeah, that's a question, Suresh. What are the different techniques available to reduce the shrinkage stresses?
See, this is the field related one. I can say some of the suggestions. Uh, During the construction, you need to take care of the water content. The first main important is the water content, or what water content you are constructing, and then the temperature, at what temperature you are maintaining to during the construction itself. Otherwise, due to the say there are high temperatures, like in the daytime, you are casting the slab. There is a temperature variations are more, air temperatures and this one. So the temperature difference of the air temperature and the casting temperatures will be less, so that the shrinkage cracks can be lowered. In the design in this model, it's not taken care of this. I think yesterday Reddy sir was saying that there is a 5-degree curl will be taken care in the 2015 revision. This is because of this one only, because of the that shrinkage. The slab itself will be after casting, when it is hardened, then itself it will curl will be there. Means temperature gradient already it will be there in the slab. Yeah.
Actually, in the afternoon, also we have a session exclusively on the concrete mix designs and casting pavements and how to control this water cement ratio. All those things. You can, of course, ask these questions in the afternoon session also. Okay, let me conclude today's second session. Actually, Mr. Suresh, who is working as a director um, in Samath Infra Inc. Technocrat Private Limited, Hyderabad, which is also one of the, I can say, very good consultancy company. So, working in the areas of transport, different areas of transportation engineering. So, coming to this presentation, like Mr. Suresh has started this presentation by explaining various types of stresses developed in rigid pavement due to wheel load, self weight of slab, and temperature. Mr. Suresh had explained the complete development of equations for calculating stresses in rigid pavement and what are the limitations in it. And Suresh had nicely demonstrated how to construct the FU model with different elements, different elements for analysis of stresses in rigid pavement with various combinations. It has shown the results of finite element analysis uh, with various combination of loading and of course the temperature and, and they have how they have validated. At the end, this is another very important aspect I like from this presentation. At the end, he had thrown some light on various areas that definitely need the research or further study. So I thank Suresh for your wonderful lecture again. And when I asked Suresh, immediately he said, I have not delivered any such type of, because you are field engineers and you should come forward and deliver. Definitely we will provide the opportunity. We at Academic Institute, we provide the opportunity. You please come and come forward and deliver such lectures. And planning to soon planning to conduct one more program on exclusively on bituminous pavements, right? So definitely I'll invite in that program also. I request you also come and deliver the lecture, right?
Yeah,
Thank you.
thank you. Thank you, Dr. Amar. I would like to tell you some points on you. He is my senior in diploma also. He is the 92 batch and I was the 93 batch. From that time, I know him and we traveled, and
Yes,
again we met in the IIT Kharagpur. He is my senior there also.
yeah,
And it's a good opportunity which you given to me to deliver the lecture on stresses.
it
The
was wonderful.
fundamentals, what I given in this, these are the fundamentals of how to find out the stresses by using the finite element methods.
I request participants, so Mr. Suresh found some of the areas which need immediate research. So if you are interested, you please carry out the research. And if you have any doubt, you talk to Suresh. About 2 months, 2 or 3 months back, we both also discussed, and Suresh said he told me that he wants to construct some pavements. Of course, we both have decided to construct some test sections at different locations, different parts of the country. Suresh, actually, if you can see in our FDP, uh,
Yeah.
participants are from all 29 states. All
Oh,
29 states. Yes,
yeah,
actually,
yeah,
we have even like our AICT has limited the number of the participants to 200, but
okay,
we have taken little bit more than we have asked the permission for accepting more number of the
okay,
participants, 10% more only. So
okay.
mainly to accommodate the participants from different parts of the country, all the states, different parts of the
Yeah,
country that we have accommodated. So this is also like anyway, I will be in touch with them. We have the contact numbers of each and every participant. So whatever the idea that we have, construction of test sections at different parts of the country, so that we will get the realistic data related to the temperature. That will be
yeah.
definitely useful for developing such kind
Yeah,
of.
because we cannot correlate with the air temperature with the with the temperature of the concrete slab. So because of that one, yes, the research is required on the temperature gradients on the concrete pavements.
Oh, okay, Suresh, right.
Yeah, thank you one and all for patience of listening. Thank you.